Nobody told you the truth about the Big Bang, not your textbooks, not the documentaries, not the professors who should have known better, standing at their whiteboards drawing a dot and an arrow and saying, it all started here. That picture is wrong, not approximately wrong, not wrong in a few details wrong, fundamentally, structurally, almost comically wrong. And the worst part is that we've known it was wrong for decades, and we just kept showing people the dot and the arrow because the real answer is harder to draw. So let me draw it for you the right way, and I'll warn you in advance, you're not going to like some of what I tell you. I don't mean you'll find it upsetting. I mean, it's going to bump up against the part of your brain that needs things to make intuitive sense, and that part is going to resist. That's fine. That's what thinking feels like. Stay with me. Here's where we have to start. When most people hear the Big Bang, they picture an explosion, a point of matter or maybe a point of energy, for the more sophisticated among you, sitting in some pre-existing space, and then boom, it expands outward, filling that space, the way a firecracker fills a room with light and sound. That's the picture. That picture is wrong on every single level, and I want to dismantle it piece by piece, because the truth that replaces it is so much stranger and so much more interesting that it deserves to be understood properly. First, there was no pre-existing space. Space itself was created in the Big Bang. This isn't a poetic statement. This is a precise mathematical claim that comes directly out of Einstein's general relativity, which has been tested to greater precision than almost any theory in the history of science. Space is not a stage on which the universe performs. Space is part of the performance. It is a dynamic, physical thing. It can stretch, it can curve, it can oscillate. And 13.8 billion years ago, there was no space, there was no outside the universe where the explosion happened. There was nothing, and then there was something, and the something included the space it was expanding into. When you ask what did the universe expand into, you're asking a question that has the wrong shape. It's like asking what's north of the North Pole. The question assumes a geometry that doesn't exist. Second problem, there was no before. Time, like space, is a physical thing, and if general relativity is right, and it is right, everywhere we can test it, then time was also created at the Big Bang. Before the Big Bang isn't a place we can't see. It is a phrase that refers to nothing, the way north of the North Pole refers to nothing. There's no before any more than there is an outside. This is not a limitation of our instruments. It is a statement about the structure of reality. Now, here's where it gets strange. Because if I'm telling you that space began and time began and there was nothing before then, I've walked you to the edge of a cliff and I owe you an account of what's at the bottom. What does it mean for time to have a beginning? What does it mean for something to come from nothing? These are not just philosophical questions. They are physics questions, and they have physics answers, partial answers, contested answers, answers that keep me up at night, but real scientific answers that we can calculate and argue about and test, at least indirectly. Let me back up and tell you how we know the universe had a beginning at all, because this was not obvious, and the story of how we figured it out is one of the great intellectual dramas of the 20th century. In 1915, Einstein published general relativity. It was immediately clear that his equations permitted, in fact, seemed to demand a universe that was either expanding or contracting. Einstein himself found this so physically unacceptable that he added an extra term to his equations, a cosmological constant, specifically to force a static universe. He later called this the greatest mistake of his career. He was right to call it a mistake, though as it turns out, the cosmological constant has come back to haunt us in a different context, and that's a story for another day. In 1922, a Russian mathematician named Alexander Friedmann, working purely from Einstein's equations, without any observational data, derived the first rigorous mathematical model of an expanding universe. Almost nobody paid attention to him. Then in 1927, a Belgian priest-physicist named Georges Lemaitre independently derived the same result and connected it to the observations being made by Edwin Hubble at the Mount Wilson Observatory in California. The galaxies are moving away from us, and the farther away they are, the faster they're receding. Hubble published the observational data in 1929, and suddenly the implications were unavoidable. If everything is flying apart now, then in the past everything was closer together. Run the movie backward far enough, and you get to a moment when everything was in the same place at the same time. Lemaitre called it the hypothesis of the primeval atom. He imagined the entire universe compressed into a single quantum one atom containing all of space and time and matter, and he suggested that the Big Bang was the radioactive decay of that primeval atom. He wrote about it as far back as 1931. The physics wasn't quite right, but the basic instinct was extraordinary. He was 40 years ahead of where the rest of cosmology would eventually catch up. And here's what I want to pause on, because it matters. Lemaitre was a priest, a Jesuit-trained Catholic priest who held a doctorate in physics. And he was the one who had to spend years fighting off the Pope's enthusiasm for his discovery. Pius XII loved the Big Bang. He thought it confirmed Genesis, let there be light, and Lemaitre, to his enormous credit, kept telling the Vatican to stay out of it. He said explicitly that the Big Bang was a scientific hypothesis about physical origins, not a theological statement about ultimate origins, and that conflating them would damage both science and theology. He was right. I bring this up not to be provocative, but because the man who identified the beginning of the universe also understood better than almost anyone that identifying a beginning doesn't answer the question of why there is something rather than nothing. That question goes somewhere else, and we'll come back to it. Now, the Big Bang model, the hot, dense, expanding early universe, is not a hypothesis. It is confirmed by three independent pillars of evidence so strong that the combination of them would constitute proof by any reasonable scientific standard. First, the expansion of the universe, which Hubble observed and which we have now mapped in extraordinary detail. Second, the cosmic microwave background radiation, the afterglow of the Big Bang itself, predicted by George Gamow and Ralph Alpher in 1948, and accidentally discovered by Arno Penzias and Robert Wilson in 1964, for which they won the Nobel Prize. They thought it was pigeon droppings in their antenna. The universe's birth certificate, and they thought it was pigeon droppings. Third, Big Bang nucleosynthesis, the prediction that the early universe, for its first few minutes, was a nuclear furnace that forged the lightest elements, hydrogen, helium, and a little lithium, in precisely the ratios we observe throughout the cosmos today. The match between theory and observation is better than 1 part in 10,000. The Big Bang is not in doubt. What is in doubt, what is, in fact, deeply mysterious and unresolved, is what happened at and before the very beginning. And this is where the picture gets genuinely weird. Here's the problem. When you run Einstein's equations backward toward the beginning, something breaks. At a certain point, about 10 to the minus 43 seconds after the beginning, a time we call the Planck time, the density and the temperature reach values so extreme that the equations themselves stop working. They produce infinities. And in physics, an infinity is not a number, it's a confession. It's the equations telling you, I was not built for this. You need better tools than I am. At the Planck scale, you cannot ignore quantum mechanics. And here is the central, unresolved crisis of modern physics. We have two theories that together describe essentially all of physical reality, and they are fundamentally incompatible. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes everything else at the smallest scales. Both are correct in their extraordinary precision, and they cannot both be right at the same time in the same place. The mathematics simply doesn't work. At the Planck scale, at the very beginning of the universe, gravity is so strong that you need general relativity, and the scales are so small that you need quantum mechanics, and the fact that those two theories don't fit together is not an inconvenience. It is the central problem of fundamental physics. This is the problem I've spent most of my career working on. Not directly, I came to it through string theory, through the attempt to build a unified framework that could speak both languages simultaneously. And I want to tell you something about that journey because people have a cartoon version of it in their heads that I'd like to replace. When I first came to string theory in the 1970s, and I mean the early days, when the field was mostly a handful of people in basements arguing about whether a theory of one-dimensional vibrating strings could make sense of the strong nuclear force, nobody thought of it as a theory of quantum gravity. That came later, and it came as a surprise, the realization that string theory automatically included a particle that behaved like the graviton, the quantum carrier of gravity, was not expected. It landed in our laps, and for a moment, we thought we had the answer. We thought we were holding the theory of everything. What we actually had was the beginning of an argument with the universe that is still going on. Here is the part that took us another 2 decades to fully understand. String theory doesn't give you one universe. It gives you a landscape of possible universes, each one corresponding to a different way the extra dimensions of string theory can be curled up and configured. The number of these possible configurations is staggeringly large. Some estimates put it at 10 to the power of 500. That's a number. That's a number that would take more digits to write out than there are atoms in the observable universe. Each configuration gives you different physical constants, different particle masses, different laws of physics. In some of them, the electron is heavier. In some, gravity is stronger. In some, carbon chemistry doesn't work, and life as we know it is impossible. Now, I want to be honest with you about what this means and what it doesn't mean, because people on both sides of this argument have been less than honest, and that's something I don't have patience for. What it does not mean is that string theory predicts anything goes, or that we can tune the parameters any way we like. What it might mean, and this is genuinely contested, genuinely unsettled, is that all of those configurations are actually realized somewhere in a collection of universes we call the multiverse. And our universe is simply the one we happen to find ourselves in, partly because its physical constants are compatible with the existence of observers like us. This is called the anthropic principle, and I have complicated feelings about it. Not because I think it's obviously wrong, I don't, but because in its weak form, it's trivially true, and in its strong form, it risks becoming the kind of explanation that looks like an explanation, but actually explains nothing. That's a line I watch carefully. But before we get to the multiverse, and we will come back to it, I need to tell you about inflation, because inflation is where the real action is, and it is simultaneously one of the greatest ideas in the history of cosmology and one of the most underappreciated. People know the word, they don't know what it means or why it matters. In 1979, a young physicist named Alan Guth was working at Stanford Linear Accelerator Center trying to understand a problem called the magnetic monopole problem. Don't worry about what monopoles are. The point is that the standard Big Bang model predicted we should be swimming in them, these exotic particles left over from the early universe's phase transitions, and we observe essentially none. Guth was trying to figure out where the monopoles went. What he discovered in the process was something much bigger, a mechanism that could solve not just the monopole problem, but 3 other serious problems with the standard Big Bang model simultaneously. The 3 problems are these. First, the horizon problem. The cosmic microwave background, the radiation left over from when the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, is extraordinarily uniform. The temperature is the same in every direction, to better than 1 part in 100,000. But here's what's strange. Opposite sides of the sky, separated by billions of light years, could never have been in causal contact with each other in the standard model. There wasn't enough time, so why are they at the same temperature? If 2 regions of the universe never talked to each other, never exchanged any signal, never had any physical interaction, how did they end up at the same temperature? This is the horizon problem. Second, the flatness problem. The universe is spatially flat. The angles of a triangle in the universe add up to exactly 180 degrees. To the precision we can measure, this sounds innocuous, but it's actually a knife-edge condition. General relativity tells us that the density of the universe determines its geometry. If the density is slightly above a critical value, the universe curves back on itself and is closed. If it's slightly below, it expands forever and is open. The fact that the universe is flat means the initial density in the earliest moments had to be tuned to extraordinary precision, something like 1 part in 10 to the 60. That's not a coincidence. That's a conspiracy. The universe didn't pick that number by accident. Something selected it. Third, the structure problem. The universe is not perfectly uniform. There are galaxies and galaxy clusters and giant cosmic voids, structure on every scale. Where did that structure come from? The standard Big Bang model needs it to be there as an initial condition, baked in at the beginning, and that's not an explanation. That's just pushing the question back a step. Guth solved all 3 problems in a single stroke. His proposal, in the first tiny fraction of a second after the Big Bang, we're talking from roughly 10 to the minus 36 seconds to 10 to the minus 32 seconds, intervals that would take 10 lifetimes of the universe to write out in standard notation. The universe underwent a period of exponential expansion so violent that a region smaller than a proton expanded to a volume larger than our observable universe today. Not just rapidly, exponentially, doubling in size with every tiny tick of a clock that was ticking unimaginably fast. During inflation, any curvature the universe had before gets stretched flat, the way blowing up a balloon smooths out the wrinkles. The horizon problem is solved because all the regions of the universe we can observe today were once so close together that they had plenty of time to come to thermal equilibrium inflation, then stretched them to opposite ends of the sky. The flatness problem is solved because inflation drives the geometry relentlessly toward flatness, no matter what it started as. And the structure problem, this is the beautiful part, the structure problem is solved by quantum mechanics. Here is where quantum mechanics and cosmology shake hands for the first time, and I want you to feel the weight of this moment. During inflation, the quantum vacuum, the lowest energy state of space, is not smooth. It is seething with quantum fluctuations, infinitesimally tiny ripples in the energy density. Normally, these fluctuations appear and disappear, virtual and ephemeral. But during inflation, the expansion is so rapid that it stretches these fluctuations out before they can disappear, freezing them into the fabric of space-time. These frozen quantum fluctuations become the seeds of all large-scale structure. The galaxies, the galaxy clusters, the cosmic web, all of it traces back to quantum noise in the vacuum of the earliest universe, amplified to cosmic scales. We are all descendants of quantum fluctuations. And here is the extraordinary thing. This is not speculation. We can calculate the statistical pattern of these primordial fluctuations, their power spectrum, the way their amplitude varies with scale, and compare it to the observed pattern of temperature variations in the cosmic microwave background. The prediction and the observation match. We have satellite missions, COBE, WMAP, Planck, that have mapped the temperature of the cosmic microwave background across the entire sky with extraordinary precision, and the pattern we see is consistent with the predictions of inflation, including the detailed shape of the power spectrum, including the fact that the fluctuations are adiabatic, including the fact that they are nearly but not exactly scale invariant. Nearly but not exactly. That nearly is important. If the fluctuations were perfectly scale invariant, it would suggest something specific about the inflationary model. The fact that they're slightly tilted tells us something about the physics of the inflaton field, the field whose energy drove inflation, and different inflationary models make different precise predictions about this. Tilt. This is where inflation becomes a real scientific program rather than just a beautiful idea. We can distinguish between models, we can rule some out, we can test it. The Planck satellite data, published in 2018, has already ruled out a large swath of the inflationary model space. The simplest models, the ones that look most natural from a theoretical standpoint, survive. The Baroque over-engineered models are under pressure. This is science working the way science is supposed to work. But let me tell you what inflation does not solve, because I've been too generous with it and I want to be honest. Inflation solves the problems of the standard Big Bang by pushing them earlier. It doesn't solve them, it relocates them. You still have to ask, what started inflation? What was the inflaton field and where did it come from? What were the initial conditions before inflation? Inflation requires initial conditions, and those initial conditions have to be specified. The problem of the beginning is not dissolved by inflation, it is sharpened. Inflation clears the table so that the question of origin sits right in front of us, unobstructed, demanding an answer. Here is where we reach the real frontier. And I want to slow down here, because this is territory where the physics is incomplete, where the ideas are competing and partly speculative, and I refuse to present it as though we have answers we don't have. Intellectual honesty is not optional in physics. It is the whole game. The deepest proposal for what happened at the beginning, or rather for what replaced the beginning, comes from the work of Stephen Hawking and James Hartle, who published it in 1983. I have to talk about Hawking here because I have history with him, and I think the Hartle-Hawking proposal is one of the most profound and most misunderstood ideas in the history of cosmology. Hawking and I had a long argument, years of it. Most people know about the black hole information paradox, the question of whether information is destroyed when matter falls into a black hole, and they know that Hawking initially argued it was, and eventually conceded that it wasn't. I was on the other side of that argument from the beginning, along with Leonard Susskind, and we were right, and Hawking eventually agreed. He bought Susskind lunch. He did not buy me lunch, which I think is a factual injustice, but I've made peace with it. But on the Hartle-Hawking proposal, I think Hawking was reaching for something genuinely important, even if the execution is incomplete and the interpretation is contested. Here's the idea. In quantum mechanics, we use a mathematical object called the wave function to describe the state of a system. The wave function contains the probabilities for all the possible outcomes of any measurement you could make. Hartle and Hawking proposed that the universe itself has a wave function of the universe, and that this wave function can be calculated using a mathematical technique called the path integral, summing over all possible geometries of space-time. Now, here's the revolutionary part. In their proposal, they sum over geometries in which time becomes imaginary in the technical mathematical sense of imaginary numbers near the beginning. And when time is imaginary, it behaves like a spatial dimension. The four-dimensional space-time of the universe near its origin becomes, in this description, a four-dimensional sphere. And a sphere has no boundary. A sphere has no edge. There is no singular point at which everything started. The beginning of time is replaced by a smooth, rounded surface, the way the North Pole is a smooth point on the Earth without any boundary or edge. The slogan Hawking used, and he loved it perhaps too much, was "The universe has no boundary." The boundary condition of the universe is that it has no boundary. In this picture, asking what happened before the Big Bang is like asking what is north of the North Pole. There is no before. Not because time extended forever, but because time gradually turned into a spatial dimension and the boundary dissolved. I find this beautiful, and I find it deeply unsatisfying simultaneously, and I think that's the appropriate response. Beautiful, because it is mathematically elegant, and it genuinely does, in principle, address the problem of initial conditions. Unsatisfying, because we don't know if the path integral over all geometries actually converges. We don't know if the computation can actually be done, even in principle. We don't know if the universe we get out of the Hartle-Hawking state matches the universe we actually live in. These are not minor technical difficulties. They are deep problems that have occupied some of the best mathematical physicists for 40 years. There is a competing proposal that I want to give equal time to, because it's taken seriously by serious people, and it comes from a different direction. Alexander Vilenkin, working in the early 1980s, proposed that the universe tunneled into existence from nothing. In quantum mechanics, tunneling is a real observed phenomenon. A particle can pass through a barrier that classical physics says it cannot cross, because the wave function of the particle leaks through. Vilenkin's proposal is that something similar happened to the universe as a whole. The universe tunneled from a state of nothing into a state of something, with the laws of quantum mechanics applying to the tunneling process itself. The obvious objection is, if there was nothing, there were no laws of quantum mechanics either. And Vilenkin has an answer, which is that the laws themselves, the mathematical structure, are what he means by nothing. In this view, mathematics precedes the physical universe, and the physical universe is a quantum fluctuation of the mathematical laws. I'll be honest, I find this intellectually provocative, and I'm not sure what to do with it. It pushes the question back to why these mathematical laws rather than some others, and I don't know that we have a satisfying answer to that. Let me tell you about a conversation I had years ago with a philosopher who specialized in metaphysics. We were arguing about the question of why there is something rather than nothing, and he said something that has stuck with me. He said, the question assumes that nothing is the simpler state, and something requires explanation. But maybe that's wrong. Maybe something is the default, and nothing, true nothingness, with no laws, no structure, no mathematics, is the state that requires explanation. I don't know if he was right, but I think the question of which is the default, something or nothing, is not answered yet by either physics or philosophy, and anyone who tells you it is not being straight with you. Here is another thing that keeps me genuinely, productively unsettled. I mentioned the multiverse earlier, and I want to return to it because if inflation is correct, the multiverse is almost certainly real, not as a speculation, but as a consequence. Here's why. Inflation, once started, is very hard to stop. In the simplest models, different regions of the inflating universe stop inflating at different times, and when they stop, they become pocket universes, regions of space that have settled into a low energy state. The inflating space between them keeps expanding, generating new pocket universes forever. This is called eternal inflation, and it was worked out by Andre Linde in the 1980s. If eternal inflation is correct, our universe is one bubble among an infinite sea of bubbles, each with potentially different physical constants, settled from the landscape of possibilities that string theory maps out. Now, I want to be precise here, because the multiverse is often discussed in a way that makes physicists wince. The multiverse, in this sense, is not a claim that anything goes. It is a specific physical prediction of specific physical models. And those models are testable not by directly observing other universes, which we cannot do, but by the predictions they make about our own universe. The statistical distribution of physical constants in the multiverse, combined with the requirement that observers like us can exist, makes predictions about what we should observe. Some of those predictions have worked. The value of the cosmological constant, which was predicted to be small but non-zero by anthropic arguments in the context of the string landscape, before it was measured to be exactly that. Steven Weinberg made this prediction in 1987. Almost nobody believed him. The cosmological constant was measured in 1998. He was right. Does this prove the multiverse? No. It is a successful prediction, but successful predictions can come from false theories. We have to be honest about that. What it does is raise the stakes. It means the multiverse is not obviously crazy, that it makes contact with real physics, and that dismissing it out of hand is not intellectually defensible. I want to come back to the black hole information paradox, because it connects to the beginning of the universe in a way that I think is underappreciated. When Hawking showed in 1974 that black holes radiate, that they emit thermal radiation and slowly evaporate, he created a crisis. Because thermal radiation carries no information. It is random. And if a black hole forms from some complex structured collection of matter and then evaporates into thermal radiation, all the information about what went in has apparently been destroyed. Information is gone. The universe has a fundamentally irreversible process. This violates a principle that is deep in quantum mechanics, the principle of unitarity, which says that the evolution of a quantum system never destroys information. It can hide it, scramble it, make it practically inaccessible, but it cannot destroy it. So who is right? Hawking's calculation, which says information is lost, or quantum mechanics, which says it can't be? The answer, which took 30 years and the work of many people, including Juan Maldacena's extraordinary discovery of the ADS CFT correspondence in 1997, is that quantum mechanics wins. Information is not destroyed. It escapes in the Hawking radiation, encoded in subtle quantum correlations that look thermal to any practical measurement but carry the information in their precise quantum state. Hawking was wrong about this, and he eventually agreed. But here's the thing, we still do not have a complete, detailed account of exactly how the information gets out. The mechanism is not understood. This is not a small gap. This is a gap big enough to drive a truck through. And here is the same incompatibility between general relativity and quantum mechanics that shows up at the center of a black hole where spacetime reaches a singularity also shows up at the beginning of the universe. The Big Bang singularity is, in a precise mathematical sense, the same kind of breakdown that we see inside a black hole. The physics of quantum gravity that we need to understand black holes is the same physics we need to understand the beginning of the universe. These are not separate problems. They're the same problem wearing two different hats. And this is why I believe, and I want to be clear, that this is a belief motivated by evidence and by the structure of the mathematics, not a certainty that the question, how did the universe begin, will not be fully answered until we have a complete theory of quantum gravity. We have candidates. String theory is the most developed candidate. Loop quantum gravity is another. There are others more exotic with smaller communities. None of them is complete. None of them has made a prediction unique enough and precise enough to be definitively confirmed or ruled out. This is the honest state of play. And I think it's important to say it plainly, because there is a temptation, a very human temptation, to dress up our best guesses as answers, to smooth over the uncertainty in the name of making the story cleaner. I've seen it done by people who should know better. I have probably done it myself in moments of enthusiasm. It is a failure mode I try to guard against, because the honest acknowledgement of what we do not know is not a weakness of science. It is the engine of science. The gap in our understanding is not an embarrassment. It is the most interesting thing in the world. It is where the next revolution lives. Let me tell you one more thing, and then I'll leave you with a question that I think you will carry with you longer than anything else I've said today. There is a concept in quantum cosmology called the wave function of the universe, and I mentioned it in the context of Hartle and Hawking. But I want to tell you what it implies, because most people don't follow the implication all the way to the end. If the universe has a wave function, then in principle, and this is the kind of in principle that may be forever beyond practical reach, the entire history of the universe, from its beginning to its end, is contained in that wave function. Every galaxy, every star, every planet, every organism, every thought, ever thought, all of it encoded in the quantum state of the universe. The universe is, in this sense, a quantum system like any other, except that there is no observer outside it to measure it. And here is the thing that genuinely unsettles me, even after all these years. In quantum mechanics, a system does not have definite properties until it is measured. The act of observation, the interaction between the system and an observer, is what selects one outcome from among the many possible outcomes encoded in the wave function. This works beautifully when the system is an electron and the observer is a physicist in a laboratory. It does not work at all, or at least we do not understand how it works when the system is the entire universe, because there is no outside. There is no external observer, and yet the universe appears to have definite properties. Galaxies are in specific places. Particles have specific masses. Everything seems perfectly concrete and specific and real. Why? How does the universe happen without an external observer? This is the quantum measurement problem applied to cosmology, and it is one of the deepest unresolved questions in physics. Hugh Everett proposed in 1957 that the universe doesn't collapse into one outcome, it branches. Every quantum event produces every possible outcome, each in its own branch. In some branches, the electron went left. In others, it went right. All branches are equally real. This is the many worlds interpretation, and it is taken seriously by serious physicists, not as a metaphor, but as a literal claim about the structure of reality. It is also deeply unsettling in ways that I find hard to articulate precisely, which is itself a kind of data point. What I can tell you is this. The universe began in the sense that there is a finite past, a direction in which the cosmos becomes younger and denser and hotter, with a limit that our current physics cannot penetrate. The Big Bang is real. Inflation almost certainly happened. The universe is 13.8 billion years old, and its history is written in the microwave background and in the distribution of galaxies and in the abundances of elements, and we can read that history with remarkable precision. All of that is solid. What is not solid, what is genuinely open, genuinely contested, genuinely exciting, is the question of what happened at the very beginning, what kind of quantum state the universe tunneled or evolved from, whether there is a multiverse, whether the laws of physics are fixed or vary across the landscape, and why quantum mechanics and gravity refuse to shake hands. These are not questions at the edge of physics, they are questions at its center. They are where all the action is. So here is what I want to leave you with. Not a summary, not a conclusion, but a live wire that I am handing you and asking you to hold. The universe is 13.8 billion years old. It began in some sense that we do not fully understand from a state that our physics cannot fully describe. It expanded and cooled and formed galaxies and stars and planets, and on at least one of those planets, it formed creatures who can ask why. That is not a small thing. The fact that the universe has produced beings capable of doing physics, capable of staring back at the beginning and trying to understand it, is not incidental. It is the most extraordinary fact I know. But here's the question I want you to carry. If the universe began from a quantum state, from a no-boundary condition, or from a tunneling event, or from whatever the correct description turns out to be, then the beginning of the universe was a quantum event. And quantum events don't have causes in the ordinary sense. They have probabilities. They are selections from a distribution of possible outcomes, governed by the wave function. The universe did not happen because something caused it. The universe happened because it had a non-zero probability of happening, which means the question, why is there something rather than nothing, might have a quantum mechanical answer, not a cause, not a reason, just a probability that is not zero. And if that's right, if existence itself is a quantum fluctuation, then the question is not, why does the universe exist? The question is, why does this universe exist? Why these laws, these constants, this particular selection from the landscape of possibilities? I don't know the answer. Nobody does. And I've spent 50 years working on the tools we'd need to find it, and we're not there yet. Maybe we'll get there. Maybe the answer, when it comes, will make everything we think we know look like the pigeon droppings on a radio telescope. That's happened before. I have every reason to believe it will happen again. I'm not troubled by that. I'm exhilarated by it, and if you're not, I'd check your pulse.